Hey, welcome, thank you. My name is Dan Ferber. I'm a solution architect at Intel. This is Carl Vietmeyer. Carl's also a colleague of mine, a solution architect at Intel. We're going to go through some IOPS-based low latency Ceph configurations and workloads. I'll do a couple intro slides here. Carl will go through the data. And then Tushar Gohad, whose name you see up here as well. He's a principal engineer at Intel, and he'll be here for the Q&A. So I think we're going to have time at the end for a good deal of Q&A, and then Tushar will join us for that. Yeah, this is what I'll go through. I mean, I'll walk through just a couple of objectives, then Carl will walk us through the config and the performance. But just before I go through the objectives, though, and apologies if any of you have seen this before, but I mean, Intel is fairly active, as I'm sure probably a number of you are, in the Ceph upstream community. So this is just a look over time of not all of the things Intel's done. I mean, you can go look for all of it, but this is some of the more significant things that when I talk to the community, they're interested in. And the pattern here, obviously, is we try to make Ceph go really, really well on Intel platforms. But in general, that pretty much means any platform. So most of the work we do, it's all upstreamed, it's all in the open, and pretty much it's all good for everyone in the community. The focus is around performance. So we work on performance on processors. We work on things like OSD restructuring and threading, and we work obviously on performance to SSD and NVMe devices. So just a quick look, and so it's in the video and in the slides. So what we're going to go through here today are configuration that we put together, an all NVMe configuration with a 3D Crosspoint or an Optane journal. Carl will walk you through that. And really it's for workloads that are IOPS and latency sensitive. So database would be the typical kind of workload that you can put on Ceph. And then this morning, just to call it out, Carl and Tushar and one of our colleagues from AT&T did a presentation on disaggregated Ceph performance. And so you can, if you weren't able to attend that, you can look at that. That'll be on video. And there you go. Thanks, Carl.
Thanks. So if anyone was in the session this morning, we talked about some future work, things like BlueStore and NVMe and Optane journals. Well, this is the future work that we referred to, essentially. I mean, the things we talked about. Well, hyperconverged futures, but this configuration would be applicable to a hyperconverged architecture as well, right? But yeah, this is disaggregated, not hyperconverged. But some of the things we talked about doing in the hyperconverged, we've done here. Because in the earlier session, it was co-located journals, no Optane caching, and it was file store. So this is the wall and DB on Optane and BlueStore. So just a couple things. So as we look at how Ceph has performed over the years, Ceph's been around for a little while, and we're talking about things. When we talk about software-defined infrastructures and storage, we talk a lot about data center modernization, and so when we think, very few people deploy things on old servers. So I just want to kind of show that over time, from Haswell through Broadwell to Skylake, there's just been a general improvement in performance, and this is the kind of the Intel story, really, as we move forward to different platforms. So performance goes up, latency goes down. And that's without any of the improvements. Of course, if you think about Haswell, right, we didn't have things like 3D NAND and 3D Crosspoint, right? It was just standard NAND, or if we even used NAND much at all, those were mostly hard drive configs. And then the random write performance, same thing. IOPS goes up, latencies go down across the generations. So then the other thing we're going to talk about today is the two NAND technologies. There's really two basic types of NAND now on the market. And I don't know if you can 3D is 3D Crosspoint really NAND? But there's really two. There's 3D NAND, which is we move from a 2D planar to a 3D because we just couldn't stuff any more data on that 2D plane. Just like when hard drives went to multiple platters, same concept really. Just how do I fit more stuff in the same square meter, square inch? Just go vertical. Just add the y-axis. So we get, that's kind of oversimplification. There's a lot of improvements in the controllers. So we have higher endurances and lower latencies and higher performance. But in general, we move to a 3D so we can get to much denser. We can go 4, 8, and even 16 terabytes per drive. And then the 3D Crosspoint, which is what we call Optane. This is a whole different technology. With 3D NAND, it's still NAND. You still have NAND controllers. You still have page writes. You still have the same, read, read, erase, write cycles. You still have garbage collection, asymmetrical reads and writes. All the things we're used to. With 3D Crosspoint, you're writing. So everybody's a little cagey about the actual details, but essentially, you remove those gates and you write directly to the cells. So you eliminate any of those things like the asymmetrical writes, garbage collection. You don't have to do that page erase anymore, which is, if you think about it, it's a lot like the bad part of RAID 5, read, modify, write. So it's much simpler. So the 3D Crosspoint, very low latency, very high performance, but not as dense. So let's look at the cluster. So what we built, so it's a little bit different than the one we talked about this morning. So this cluster that we built was built on Luminous. So it was 1-175 Luminous with BlueStore. So we used a 2x replication pool. And we'll talk about that a little bit later. Or maybe we should talk about that now. The thing about a configuration like this, when we're doing with BlueStore, and it's because it has the checksum. So there's object level checksums in BlueStore, which allow us to have a much better, let's say redundancy is probably the wrong word. It's a robustness or a lot more availability within the system, so you can get away with 2x replication instead of 3. So that's always been one of the problems, right, with software-defined storage. I used to work for NetApp, and if someone told me they only had 33% usable storage, I'd be all over that. Right? Because that's pretty bad. 33%. If I need a petabyte, that means I need 3. Well, this way, you can really, it's like mirroring. So much more efficient from a space perspective. This is going to help bring that price per gigabyte down for the total configuration. If you look at price per gigabyte per drive of a flash solution, that price per gigabyte per drive, absolutely, the numbers are way off from a hard drive. But if you start looking at things where, okay, we can do 2x replication instead of 3x, we can use fewer drives than we would with hard drives, the numbers start to change a little bit and start to get closer to realistic as far as having an economical, all-flash, capacity-based solution. So here what you're seeing is, but we're only using 4 drives here. So we have one P4800, that's our Optane, or our 3D Crosspoint journal. It's small, 375 gigabytes, and then 4 terabyte SSDs, NVMe SSDs, and then 2 dual 25s, so that's 50 gigabits per second of network. 100 total, but we bonded them up for redundancy, so that's 50 usable. So pretty good configuration, 6 nodes. How many clients did we have? We had 6 clients, 6 storage nodes. Pretty. And then our clients were still Broadwell, but the clients aren't nearly as important as the cluster nodes. And then also note 2 separate networks. This question was asked this morning. So we did do separate networks. So separate client, separate network, replication network, which is a standard best practice for Ceph. So what do we see? What are some of the things we saw? Well, if you look at something like this chart here, where we're showing your latency versus IOPS and some of the scaling, this would be, with BlueStore, you'll notice that we can scale out to almost 2 million IOPS and 700K, 320. Just the 4K. And then, so scaling, we're going to scale our storage, so 2 vectors. So the things we scale are, we co-locate journals. collocate multiple OSDs on a single NVMe. So this was another thing that came up this morning was, multiple OSDs help scale the system as far as threading. So more OSD processes, you have more threads, more simultaneous I/O. But if you have only a few NVMe drives, you only get to have a few OSDs. So the idea is, well, how can we add more, keep that number of OSDs up, which is stack multiple NVMEs on a single, multiple OSDs on a single NVMe, or add more NVMe drives. So kind of two things, right? Scale more NVMe drives. Maybe we don't want to add more drives. Maybe we want a smaller number of denser drives. So kind of, it's a balance. So what we see with that is that if you'll notice, for example, the green line there, that's four OSDs per NVMe. Orange is 2 per, and orange, kind of burnt sienna, I guess, would be the crayon color for that middle one. Right? So it's 1, 2, and 4, basically. And this is what in our testing, that's what we did. So we had 1, 2, and 4. And then you'll see there's a basic standard scaling that we'd expect in any Ceph performance analysis. So, and we're CPU utilization up to 70% at the 4. So as you go to more OSDs, you're consuming more CPU. That middle ground, that's a pretty nice sweet spot right in there. And then when we look at, if we kind of break it down, we start looking at things like our 4K random reads and CPU utilization and compare those. We're and look at our IOPS. Pay attention to that the middle there. So you'll notice there's the 4, 6, and 8. That's the number of drives. And then the 1, 2, and 4, that's the number of OSDs per drive. And you'll notice with the Q depth of 8, it's kind of flat across. Sweet spot's kind of in the 6, 2, right? So 6 drives, 2 OSDs per drive. Gives you 12 OSDs per system. Nice balance. But still, it's not that much of a difference from the 4 2s, pretty close to the same. You're really getting more capacity when you move to that 6, 2. But the 2 OSDs, you notice if you go to 4 OSDs per drive, it goes down on each of these. So your 4K random reads, for example, your IOPS drops a bit when you go to that. So you're not really gaining anything by going from 2 to 4 OSDs per drive. So that 2 OSDs per drive looks like a nice sweet spot, and then you're just adding drives to scale. So then it becomes just a price per gigabyte and a capacity exercise. And that's the same really if you look on the right there with the 4K random reads with CPU utilization. Same type of, you'll see it's just pretty flat across. So you're not really consuming a lot more CPU, so it really does come kind of back to a performance per capacity exercise and discussion. So if you look at our 4K, and we're going to walk through and just look at 4K random reads, 4K random writes, same type of pattern, right? Same type of pattern. Going from that 2 to 4 to scale by adding more OSDs, not really helping us. Going from 1 to 2 helps quite a bit. You see you get a nice bump there. So that 2 is just across all of these patterns is really right in that sweet spot. And you'll see that across all of these. Now on our large block sequential, at high Q depths, we really, fewer OSDs, fewer NVMEs. Kind of makes some sense if you think about what's happening, less concurrency, more serialized I/O, so fewer devices, right? More devices aren't really going to help you in that case, which is pretty much what we expect. And then at Q depth of 8, once you get your Q depth start to go up, your network starts to impact you. At some point, you're going to move the bottleneck somewhere else. So in a system, in a setup like this, we're shifting bottlenecks around. So hard drives, we're always limited by the hard drive. It's just physics, right? You think about your 10K SAS drives with 130 IOPS per drive, 100 megabytes per second, roughly kind of industry standards for those drives. Sometimes it depends on who you talk to. They might go higher, 180, but you're still fundamentally limited by what the drive can deliver. And if you just do the math on a 20 drive server, right, you can't really overrun your network. You pop a few SSDs in there, all of a sudden kind of you uncork it, and you can easily overrun a 10 gig interface, for example. So your network's going to bottleneck you in throughput. In the latency, in the IOPS case, you're really getting bottlenecked by CPU utilization more than anything, and just threading, thread contention. So if we go to our 1 meg sequential writes, again, writes are going to benefit by more OSDs in this particular run. So what about using the Optane drives or the 3D Crosspoint for metadata? So in the earlier, this morning we talked about having co-located journals in a configuration, and that'll work, right? And that is fine, but there are some benefits to be gained by using. And what we saw from our testing was that by adding that extra journal log, well, we won't call it a caching drive really with BlueStore. Journaling's not really the correct term anymore. About 25% more IOPS for small block random writes. 50% throughput. So you're getting nice increase in throughput and IOPS by adding that in there. And you can bring those latencies down. So there's a nice, you do get a benefit. So you would think that, oh, well, we don't need it, but the way BlueStore is structured, the way it's worked, you've got your DB in your wall, you're writing separately. There's still 2 separate streams. So your metadata writes, right, your caching, it can benefit from that. And yeah, the latency, and I don't have the numbers on it in this presentation. That wasn't really a presentation about the media itself, but the latencies and IOPS, I think the IOPS on an Optane driver are somewhere around 900,000 per device. I mean, at that point, it's kind of, you have so many IOPS that it doesn't really matter at that point. And then BlueStore and Optane. So yeah, this is just shows proof, evidence of the previous claims. As you can see, that without Optane, our average latency, the curve's a little bit higher. So we're starting out a little bit higher and we're peaking a little bit higher. So you get a benefit. In every workload, maybe it doesn't matter, but if you're chasing long tail latencies, right? If we're chasing latencies sub-millisecond, right? We want deterministic long tail latencies, then the Optane could make the difference. I'm not saying in every use, again, this is data that you can use to kind of support what you need to do if you're trying to size or dimension a system. So not in every case, but there are going to be those cases, again, if you're chasing those long tail latencies and you need to be in those sub 10 milliseconds, 5 to 1 millisecond ranges, then the Optane can make a difference. Not every workload needs that. So OSD scaling. Just wanted to show this here that, again, kind of back to what we were talking about before, another way to look at it, that look, right performance in the scale, more devices, co-locating OSDs, we can get more IOPS, but there are thresholds and there's things that really don't help us much. So you'll notice going from 4 NVMe per node to 8 NVMe per node. So the light blue to dark blue, big bump, right? You get a big jump. Of course, we're doubling the number of devices. So we can double the amount of concurrency we can support. But adding more OSDs to those devices isn't giving us. So adding 2 OSDs per NVMe in the first case moves us to the right quite a bit. We move from 150,000 to a little over 200,000 IOPS. And our latency curve's a little better. So we're getting a nice bump for that. But notice that the 8 drives, adding additional OSDs if I have 8 devices isn't helping me at all. So that 8 OSD, right, the 8 OSDs, not devices, but 8 OSDs seems to be another one of those sweet spots. But yeah, so notice that we have 4 to 8. I can double the number of devices, but I just doubled the amount of cost in my system by doing that. But if I can keep that same 4, double the number of OSDs per device, and I can increase my performance without increasing my cost in the configuration. So there's ways you can kind of tweak the system and play with it to get more performance out of it without increasing cost. So summary, latest SSDs, right? Again, it's pretty obvious from our testing, definitely some improvement. It's not going to help every workload. It always comes down to having the right tool for the job, right? And so if you need it, it's available. It's possible to configure a system. So this is the thing. So Ceph has always been challenged in the latency and deterministic latency area. You know, I mean, with an all hard drive system, you know, you're pretty lucky to get latencies in the 15 to 20 milliseconds. I mean, you can work hard and get them down there, but the minute you get into a backfill situation or something goes wrong, your latencies are just going to spike and they'll go nonlinear on you. But with the thing about these all flash with an Optane or, you know, some kind of a NAND journaling, you can go after those latencies that you hadn't been able to before. I mean, no one would have ever thought with, you know, Hammer, right, and a bunch of hard drives that you would be able to support an OLTP database, transactional database, MongoDB or something like that. But with today's configurations, with an all-flash configuration configured properly, you can start to think about that. You can start to think about supporting those types of workloads, which you wouldn't have been able to touch before. Which is, you know, it's kind of, well, what do we call it? It's expanding the reach of Ceph, really. I mean, we're really expanding the scope of workloads that Ceph can support, especially on that. I have a diagram I put together, which is a bell curve, right? And this bell curve on the right is large scale out, you know, 2 to plus petabytes, and where latency isn't matter, it's all throughput. And on the left of that, the long tails on that side are low latency. And Ceph has always played in that kind of middle ground, right? If you look at that bell curve between in the, you know, 500 terabytes, 1.2 petabytes, that kind of general kind of middle range, latencies are okay, good enough, right? You've never really, before we weren't really able to chase those workloads that sitting out on that left side, that long tail of the curve. But with an all-flash configuration set up like we have here in this testing, you know, you can realistically start to think about, you know, increasing the envelope and moving out onto that left side. Just, you know, moving out to the right side, that's a whole different conversation, right, about Rados gateway and configuring using large, dense systems. But we're really focused on designing and building smaller, denser, high-performance, very low latency clusters, which in a hyper-converged environment, that starts to make some sense. You know, if you're needing to deploy very compact systems, maybe one rack of systems out in a MITSO or something like that, or a CO, maybe you need it on NEBS hardware, right? Then you can start to think about building those types of systems with Ceph to support those types of environments. And so that's, I mean, probably let you guys get out a little early. But.
Well, so you can take some questions.
Yeah.
Plus, if any of you have questions, not just on the data, Tushar, here you go in case there's questions for you. If you can also, you're also welcome to ask questions about the development. Tushar is Intel's lead Ceph developer and leader if you had any upstream development questions.
Do you have any benchmarks that show performance impact if you need to rebuild a disk?
So no. So that's if I was going to have I should have my list of things, you know, things to do. So that's definitely on our list. So, you know, we need to get a baseline, right? I mean, and so all the work kind of up till now, and a lot of this work has been, let's get a baseline, let's figure out what the system can do, let's find the edges in the middle, I like to say, right? And now we can, now that we have it and we know what that is, we have something to compare against. Now when I have my 6-node cluster and I'm cranking it 100%, yeah, I drop a node, what happens? What happens?
Tushar,
right?
yeah.
Yeah.
So that's on the, yeah.
Yeah, so we don't have it as part of this deck. I mean, we have some data which is not public yet. So we will.
Oh, then, yeah.
We'll publish through some forum. You'll see it published. So yeah. So I think there's one person on my team working on it, but she is eyeing one conference. If that doesn't go through, we'll probably come to one of these forums. So yeah.
Yeah, we want to inject failures, right? I mean, so then, but that stops being a benchmark and becomes more of a realistic test.
Yeah, so those are basically, I mean, we call that a failure mode test. You know, so we did that with hard drive as well as SSD environments, and of course the rebuild times are significantly better with NVMe's, right? So yeah, you do see different results, which we'll publish, but those are basically node network, disk failure, basically. That's what we emulate.
All the usual, right? I mean, we know what that list looks like, right?
So thanks for your talk. That was very useful and very interesting. We have quite a similar kind of test configuration to you, apart from that we're using 100 gig OmniPath for the fabric.
Oh.
Do you have any plans to evaluate that in your experiments as well?
So when you say 100 gig only, is it
the OmniPath?
Oh, OmniPath.
OPA.
Yeah.
Okay. We actually do. There was, I mean, so we're still evaluating, there's more work to be done on the Ceph side, because it's, I mean, the XIO messenger today is all, the Ceph messenger is usable, but it's not quite stable.
No, we don't use the XIO one.
Oh, okay. So how are you setting it up?
Well, at the moment we're forced to use the IP over InfiniBand. But actually, a lot of my work recently has been on the async RDMA.
Okay. Gotcha. So we're kind of evaluating both those approaches, including the lib fabrics and the IP over RDMA. It's something we need to prioritize. We just haven't gotten to it. But yeah, certainly OmniPath is one of the things we are on the roadmap this year.
Okay. Can you put me in touch with someone in Intel who's doing that work then?
It's basically me, so I'll be the guy. Yeah.
Right. Grab us afterwards.
Yeah. Thanks.
Any other? No.
Any other? All right.
Okay. Yeah, we answered all the questions.
It might be a bit of a mundane question, but what tools are you using for measuring, like FIO or?
Yeah, most of his work is actually based on emulated, workloads emulated with FIO.
Okay.
And so the Ceph community, we worked with them on this benchmarking tool called CBT, Ceph benchmarking tool, which is actually based on FIO. So it does a nice job of not just, launching, making it easy to kind of define like a simple YAML workload, but also does a very good job of collecting the data and analyzing, so it's easy to analyze essentially. And we also have another project called CE Tune, so which is basically that's a visual interface to all of this. But yeah, at the basic level, it's all based on FIO.
Yep. And is this what you're using for like filling the volumes with data beforehand, or?
Yes.
How are you initializing it? Same.
Yeah. So so all this testing was so we basically looked at the total size available. We filled it to 80%, and then that's when we ran all the benchmarks. So CBT actually does that automatically for you. So you just have to say I want 50% or 80% fill level, and it'll create the volumes, it'll fill those up, and then that's when it starts the benchmarks. Yeah.
Okay, cool.
Yeah, if you need to do CBT is definitely worth. I mean, if you need to do benchmarking with Ceph, it's definitely worth looking at. I mean, it's community supported, and it's a wrapper for FIO, and it just has a lot of facilities built in to modify configurations and makes it easy. Yeah.
Actually, with OPNFV, it was the PTL Historical project there, which is somewhat similar, but basically, using OpenStack to fire templates to fire everything up, run FIO workloads on it, and gather the data. So I want to take a look at that one and see if that's where it integrates into the NFV side.
Yeah.
So the OPNFV side, so I've been part of the team that founded the Store for NFV project.
Yes.
So I'm one of those guys, and so we've been talking. I mean, so are you? Do you say do you lead that?
Yeah, I'm Mark.
Oh, you're Mark. Okay. So yeah. So all right. So yeah, absolutely. That's the right goal. Okay. Yeah.
You don't want to use.
All right. Any other questions? Okay. Well, Carl.
Yeah, I think we're done.
All right. Okay. Thank you so much.